So welcome back. And the topic this week before the break is actually to try to finalize this discussion we had about autoencoders. And we are going to look at some of the code examples which are online on the Jupyter Notebook. In the PDF file, which you see here, I mean, it's not well displayed. So I'm just going to switch between the Jupyter Notebook, PDF, and also the whiteboard. And then I'm going to have a very, very brief introduction to transformers. And transformers is a very, very hot topic. In Rashka's textbook in chapter 16, which you have access to, you can also access the Jupyter Notebook for every chapter with codes and everything. There is actually a pretty good discussion, but the discussion is tailored to the solution of language problems. And in our case, since this course has a title, Machine Learning for the Physical Sciences, I'm actually going to give a quick discussion on how you can use transformers for solving partial differential equations. And this could be a topic for those of you who have opted for the two projects, where one of the projects, in the first project, many of you have actually looked at the physics-informed neural network for solving differential equations. But then you could actually think of looking at transformers as well to solve differential equations. And there is an example in the lecture notes, which I will just briefly mention. So this is going to be a pretty rough introduction to transformers. And then finally, we are going to, if we get time, we will start with generative models. And that means that we are going to train a probability distribution. And this is something which will keep us busy for the rest of the semester. So we are not going to talk about graph models. We are not going to talk about reinforcement learning, but the rest of the semester, we will focus essentially on generative models. And I will say a little bit, I mean, a rough introduction if we get time. So before we move on to the transformer stuff, and what's the difference between transformers and what we have done till now. So till now, we have been looking at neural networks, recurrent neural networks, CNNs, and autoencoders, which are all examples of deep learning methods. So transformers is actually something which has at its inner core, there is a deep learning method, a standard neural network or CNN or an RNN. But we are going to discuss a little bit of what's the difference between transformers and what we have seen till now. So this is roughly the layout of today. We are going to remind ourselves a little bit about the programs for autoencoders and what we have done. And then a very, very rough introduction to transformers. A very rough one. But if you wish to work with transformers, I mean, Rashka's textbook, chapter 16, which you have access to, is something which I recommend to dive into. But I will try to give you the kind of bird's view on transformers. So what we're going to do now is to actually go back to the Jupyter Notebook for this week. And we are going to look at the autoencoder codes, which is something we discussed last week. But I just wanted to recap a little bit. And now I just need to find the right stuff here. So let's go back. So what I've actually done is to run the codes before I came to the lecture here. And there's essentially one reason for that. And that is the codes are extremely slow on my laptop. And it's distressing because what you see, so this is a small aside, is that when you're going to run things like later we will look at this transformer code, which there's an example. It doesn't end during a typical lecture. And this is simply something which tells you that you need access to machine learning nodes with GPUs, etc. So if you have not done so yet, get access to the University of Oslo machine learning nodes, because that will give you access to GPUs, and you will see that that gives you a considerable speed up. So the codes which you see here, when you run them on a laptop like this one, which is 5 years old. It has an M1 processor on an Apple MacBook Pro. It's pretty slow, sadly. So machine learning, in a way, is something which many people can get started with. But when you want to run the big things, the interesting stuff, then you need access to high-performance computing facilities. And that's suddenly expensive. So if you're in your thesis project, master thesis or PhD, if your supervisors or the team you're coupled up with has access to any of the high-performance computing facilities with machine learning nodes, typically set up with GPUs, you should use them. The only thing you have to keep in mind is that you typically get charged. So like I get charged 5 Norwegian kroner per GPU hour. So if you run 100,000, that's 500,000. And it's actually eating up a lot of our research budgets. So that's the, how to say, the methods are very open. I mean, they are there. You can easily implement them. But when you want to run the bigger cases, then it's quickly something which requires lots of resources. So just a quick reminder. So the autoencoders is a method which can be used both for unsupervised training or supervised training. It can also be thought of as a generative method because with the latent space which you have and the decoder, you can actually generate new data. And it's a very powerful method. And we are going to see examples of autoencoders when they are being applied to generative models, which come a little bit later in the course after the break. But it's actually a way to encode the input data into lower dimensional representation. And as we discussed last week and the week before, there is a mathematical and very clear link between linear autoencoders and linear PCA, principal component analysis. There is actually a one-to-one correspondence, and that allowed us last week to actually, and the week before, to introduce the principal component analysis method as a way to reduce the dimensionality of a problem. So the autoencoders then has, as we said, it has an encoder part and a decoder part. So the encoder part is normally a neural network, which gets smaller and smaller in dimensionality. That means the number of nodes. And then the decoder part is symmetric. So when you pick up the data from the latent space, which you have trained, in order to reduce the dimensionality, then you rebuild the information which you had. And the hope then is that the decoder gives you something which is as close as possible to the data you gave it. So it's trained to minimize what we call the reconstruction error. Now, in the examples which we have, so this is just a simple example which you find here. This is as a typical example where we simply set up one layer. This is a simple neural network. So this is the encoder part and this is the decoder part. And as you can see, the encoder is actually the synthesis of the encoder and the decoder. This is as simple as it can be. And in this case, we actually use as an optimizer, a stochastic gradient descent. And this is the learning rate. So this is just a very simple example. But the data which is more interesting, which we have exposed you to many, many times, is the so-called MNIST data set. So this example which you find here is actually a training with the MNIST data set. And what you train then against is the accuracy. So that means the number of correctly classified numbers. And you can see now that you have so this is with TensorFlow. So we flatten the data. We have a dense layer. We have the Celo activation function. And this is the final layer, which you see here. And this one takes in, again, the same. So this is symmetric. And you can see the input shape is 30. So there's 30 nodes. And then it outputs 100. And then you have the final layer, which is a 28 times 28, which is then the standard dimensionality for the MNIST data. So it's 28 times 28 pixels. So the encoder and the decoder are actually symmetric. And with Keras and TensorFlow, it's actually pretty easy to set it up. We use the binary cross entropy in order to classify whether these are numbers between 0 and 9 and classify them correctly. And then we split the data, obviously, as you can see here, into train and test. And typically we use some 75 to 80% for training and testing. So this one is actually a stacked autoencoder with 3 hidden layers and 1 output layer. So it actually has 2 stacked autoencoders. And then you can reconstruct it. This is the training part, and then the visualization. So, and when you run these codes, you will typically see that the typical accuracy for the training here is roughly 0.97, which is not so bad. And you can see this is the examples of number you fed in, and these are the numbers which you reconstruct. So you see now that the second row here is actually the reconstructed number by the decoder. And it looks pretty close. And you see now also that you can use an autoencoder as a way to generate new images. So you can think of this actually as generated new images on which it has been trained upon. Okay? Then you can make it more fancy. So you can also actually, if you want to, you can look at the data, how they get scattered in clusters. So these are typically the correct reproduction of the data. You can replace a standard neural network with a convolutional neural network. So the thing which is nice with the autoencoders is that you have this flexibility that you can bring in any of the standard deep learning methods which we have studied. So this example now gets repeated. As I promised you, I mean, you will be exposed to the MNIST data set. So this is my lack of fantasy. According to my wife, that's a personal trait of me. So, but the MNIST data is a kind of data set which is widely used. And you will see it basically in every textbook. So I've actually taken it out so you can see it here. So now we are simply setting up a convolutional neural network, as we have discussed before. And the only thing which is done here is now that the encoder part has 2 convolutional layer, a new one. And you see that it sets up a stride, a kernel size. So that's the filter which you're setting up. The input layer is the standard 28 times 28. This is 1 color channel. This is black and white images. And then we set up the encoder part, and you will see then that the decoder part is just the symmetric one of that one. And then we set up the type of loss function which we want to optimize. Here we use Adam as an optimizer. You set up a learning rate 10 to the minus 3. So when you want to run this, you should actually have a loop over different learning rates. What you don't have here are additional hyperparameters which you can add. So you can have a norm 2 or norm 1 typical type of hyperparameters. That is not included here, but that's something which you can set up. And just to remind you, when you're setting up these networks, the only thing which gets trained are obviously the parameters of the convolutional neural network. And you see now that we are transposing it, because this is just the inverse of the encoder part. And in Keras and TensorFlow, there is a convolutional network, which is a transpose of the one you had before, because you need that one. So that brings in the symmetry of what you had from the previous case. So they are normally, when you set them up, they are just symmetric. And you could have added hyperparameters if you want to that. And then in principle, you should have a set of learning rates and then make a loop and then find the optimal result as a function of learning rate and hyperparameters. But these are parts of the setup which then become parameters which are not included in the training, like the stride, the size of the kernel, etc. This is just to quickly remind you about a convolutional neural network. And when you run this one, you see now that actually the rounded accuracy is actually better, as expected, than the one we had with a standard feed-forward neural network. And we know that from previous, when we have looked at CNNs, we know that they actually give a better training than a standard feed-forward neural network. The thing which I like with TensorFlow, although I prefer to write in normally used PyTorch, is also a simple function which gives a summary of the model, which you can see here with the encoder summary. It gives you the number of parameters, the decoder summary. There is a similar functionality in PyTorch as well. So this gives you simply all the number of parameters of the encoder and the number of parameters of the decoder. And then when you add everything up, you have the total number of parameters to train. And you see now that the first row is an example of the numbers we gave. And the second row is what the encoder, decoder produced for us. And you see now that the quality is actually much better. So this is your input. So the reconstruction error is getting pretty close to zero. And you can see that from the calculations here, that the loss function is actually much, much smaller here. And this is on the validation set as well. So you have a pretty small reconstruction error. So the thing you're training against is actually the way the images look like when you reconstruct them. And you see also that the rounded accuracy is getting close to 100%, which is pretty good. So the average, I think I once saw that the average human capability to recognize this handwritten numbers is around 98, 99%. So the CNN here is doing on average better than humans. It doesn't mean we should replace humans, obviously. That's a totally different discussion. By the way, yeah. Yeah, so I haven't done that in the codes here, but you could do that actually if you want to play around with it. So you could just ask it to generate some numbers for you. Oh, so if you look at the autoencoders and compare that with generative methods, the generative methods like diffusion models tend to do better. Yeah, yeah. And also to make new images for you. So you could actually ask it, if you have a diffusion model, you could ask it to embed it in a landscape, for instance. So that's because like diffusion models are the standard methods which enter many of these drawing programs. And this is something we will discuss after the break, actually. So in a certain sense here, what you're doing is you train on a data set, and it's not able to do anything but what you trained it on. But it will generate new numbers for you. So you can't use it as a drawing program if that's what you would like to do. No, absolutely not. And below here, you will also find an example where I just did a recurrent neural network. So with the encoder and the decoder being symmetric, and this just takes the long short-term memory. So you can actually train on such data sets. And in this particular case, I mean, you will also see that in this case, you will see that the reconstruction error for this particular case is not as good as the one we had for the CNNs. So which is in a way expected when you look at recurrent neural networks. So CNNs are really tailored to image recognition. So what I wanted to show you here is simply the flexibility you have with the autoencoders. So at the heart of it, you can actually replace the type of model or type of method you think is most relevant for your data set. Now, in the lecture notes, what you will also find is are examples which I will not be running. There's also a PyTorch example here, which basically does the same thing. And this one actually takes a standard feed-forward neural network. So there's equivalent of the first example you saw with a feed-forward neural network. And this does basically the same type of training as we saw before. So you can run it, and you can see the quality of the data which you get out. And this, you can see also the type of parameters which were used in this training. And this is the type of numbers which actually my PyTorch gives, and you see that the numbers are pretty well, pretty clear. But in this case, I actually had a much bigger network, and you see that the total number of parameters is 10 to the 5, both for the encoder and the decoder part. So this is actually a much larger network. So clearly, if you look at the Keras TensorFlow examples, I made the networks actually pretty small. There were not so many parameters. And this has actually an order of magnitude more parameters than the CNN, which you saw earlier. But this is just to give you a kind of feeling of the flexibility you have with PyTorch and TensorFlow. And the PyTorch case, if you want to use autoencoders in the second project, for instance, this is something which is pretty straightforward to implement, either with PyTorch or with TensorFlow. The nice thing with both of TensorFlow and PyTorch is that you can easily run on GPUs. So I don't have a GPU on this one, so my codes are pretty slow. And that's why I actually run them before the lecture, because it took actually 25 minutes to run all these codes. And then you guys would have been horribly exposed to all my kind of bad jokes while we were waiting for the results to end. Okay, but you see how simple it is to set it up, eh? And it's a very much used method, and I actually recommend it for many types of applications. In the so one of the things which you will also find when you go into the Jupyter notebooks, there is also an example. Let me just see if no, wait. What did I do now? Here. There should be, no, I didn't put it here. Okay, let me just leave it out. Let me just leave it. So what I want to do now is to go back to the slides and give you this promised the crash course on transformers. And then when we are done with that, we are going to, if we get time today, we will start with generative methods, which will keep us busy for the rest of the semester.
Morten?
Yeah, there's a question online here. Yeah, go ahead.
Could you talk a little bit about regularization in autoencoders?
So in the autoencoders, this is something which I didn't put in the notes here. But if you go into the textbook by Goodfellow and company, there is actually quite a lengthy discussion on regularization. Now, one thing you can add to these codes, which we have here, is actually hyperparameters. So what I did not have here, if you look at the codes, is one thing is that there is a fixed learning rate, as you can see here. But I don't have a regularization term in addition. But this is something you can add easily, both in TensorFlow and in PyTorch. So I don't have it here because when you run such a calculation like this one, you should have a grid with values of the learning rate, and you should have a grid of values with hyperparameters, the regularization term, whether you have a norm 2 or norm 1, which are the most common ones. And then you would get a set of results. You could typically have 5 learning rates and 5 hyperparameters, and you would search for the optimal values of the loss function within that parameter space. So this is fully doable, but then my program would have taken, instead of all these programs, instead of 25 minutes with 10 hyperparameters, we would say 5 hyperparameters and 5 learning rates, it would have taken me 250 minutes at least. So this is, it's pretty straightforward to actually add that in the codes here.
And the second question, if
Yeah,
you have data which have sharp gradients, so one common problem with autoencoders is that they blur things. Is there a good approach to preserving features like that in your decoded results?
I'm not sure about that actually, because this is something which I have not researched. So I will have to look it up for you, and I will try to do that. So I haven't researched that topic. So there's a question from online. I don't know if you heard the question. is the question is about whether the if you have gradients which are pretty sharp, how can that feature be preserved in the autoencoders? And this is something which I haven't done research on myself, so that means that I am on a, how to say, on unknown territory here. So my specialty or my focus has more been on generative methods, and that's where I've done lots of research in addition to using neural networks for solving differential equations. So I'm sorry, okay, but I think this is something which I can try to look up for you.
Okay, thank you.
Okay, so if we now go back to the slides, I'm going to give you this long promised crash course on transformers. And let me just find it here, and then let's just bring it up. So what we have focused on is actually, till now, typically multi-layer perceptrons or feed-forward neural networks. We have looked at autoencoders, CNNs, and recurrent neural networks. And they have specific properties. So like the feed-forward neural networks, they often deal with a dense global mixing, where you actually use dense matrices multiplied with the inputs, and you propagate that. So that means that you start with the input, and the input properties are propagated through the network. So we would call that a kind of global mixing. The CNNs, they actually look at the local properties of images. And in the filters, what you're doing now, you're actually filtering out specific properties of an image. And then you're typically making replicas of them. You make more and more replicas, and you use that as a training set. But that's also used as a way to reduce dimensionality. Now, RNNs is actually a sequential process. So the simple RNNs, which we have discussed, are pretty heavy to train. And this is probably something which many of you have seen. They keep a sequential character in the data, and they also bring in memory. So one of the problems with RNNs is typically that you would have to store the whole information if you run a simple RNN. So transformers are also deep networks. So the methods which we have seen till now are methods which we can reuse in transformers, like you saw for autoencoders, but there is a different principle. And that's something which actually becomes interesting for us. So if you think of a standard feed-forward neural network, if you look at the input, I mean, the input nodes are not connected. The nodes in a given layer are not connected. But there could be important correlations in the input data which you want to have. So to give you an example, and this is a more physics-like model. So let me just bring that up here before we move on, so that you could see an example which where you have correlations between the data. So let's just set it up here. And that's a model which we are going to look at a little bit later as well. There is actually a Jupyter notebook where you train the Ising model on transformers. So as an example of a case where you have correlations in your data set. So not all of you have met this model, but if you come from statistics or from physics, you have often seen this model. It's a spin model. It has an energy Hamiltonian, which I write as H, and in its simplest form, it's often written like this. And it has a sum over nearest neighbors, but now we just leave it like this. And there are spin values, Si and Sj. And these, in the Ising model, these are typically binary objects. So it means that these SIs, they could take values which are either -1 or +1. So this is a model which has been used quite a lot for modeling phase transitions in materials. If you take a course in statistics, an advanced course in statistics, you will often encounter it when people discuss stochastic sampling. And then instead of -1 and +1, you can find the green and blue balls, for instance, and so on. So it's a binary type of value, but you can actually extend these values of S to beyond binary. Then that leads to another model, which is called Potts model. So there's a whole hierarchy of such so-called spin models. So in physics, we normally call them spin models. Now, this J, which you see, is meant to represent the interactions between the spins. But there's nothing which hinders you to replace this with a more realistic model, where you then could have something which is given by a sum, and then you have some state-dependent interaction. Now, what you're assuming here is that all the spins or all these objects have an equal interaction parameter. But if you are more familiar with quantum mechanical representations, these J's represent integrals between interacting objects. Now, if you look at this and you're going to feed that in, so think of the S as your input data. Now, what you see now is that these J's actually couple different S's. Typically, when we have looked at a feed-forward neural network, if these S's are input data, you can see now that you could have one node which has S1, the next node has S2, etc., and there's no coupling between them. But now suddenly, we would actually like to bring in the flexibility of having some coupling. And transformers actually allow you to couple nodes in the same layers. That's one feature, okay? Which makes it quite more powerful than a standard feed-forward neural network. Now, I've online, if you look into the Jupyter notebook for this week, you will find an example which tries, with some input data, to reconstruct this value of Jij with a feed-forward neural network, which doesn't have this local information, and a transformer which has it. Now, this is also similar to another case. If you look at the gravitational potential. So if you take the gravitational potential between two particles, Rij, so this is an interaction which depends on the distance between the relative distance. This is typically given by a constant, and then it has an Ri. This is the relative distance. I'm putting these as vectors on Rj. And this is probably a formula which you have seen thousands of times. Now, in this particular case, G is a constant. But you could actually think of this as being something which would depend on the positions of the particles. But G, the gravitational constant, is a constant. So this case is a case where you could actually take, let's say, the velocities and the positions of planets, and you could use that data, the initial data, to actually, with a neural network or a transformer, to find the value of G, assuming a model like this one. So these are examples on how you can use machine learning to actually extract information about the forces which act on a specific system. And this is something which has been used quite a lot. It's actually a very interesting topic. And the first year when I taught this course, we actually had a group who spent most of the time on extracting the information about these coupling constants. So that was a small digression, which represents problems of interest in scientific, in particular in the physical sciences. If you have some forces we want to parameterize, and now I need to find back my slides. So let's go back here. So what we want is something which is called an adaptive interaction. So if you look back at that simple example, we want now the interaction to be flexible and not be just given by a constant. And this is given by adaptive interaction through attention. Now, one of the big areas of applications of transformers, which have in a way replaced recurrent neural networks. So recurrent neural networks have had a big impact on natural language processing, but transformers is the next step. And if you look at the way many of these translation softwares like Google Translate, just to give you an example, operate, they actually have transformers at their heart. So it's actually a neural network architecture built around the idea of self-attention. So I'm going to explain to you roughly what this self-attention is and what kind of parameters you need to train. So each input element can interact directly with every other input element. So if you go back to this physics-based example, I mean, with the Ising model, that's a typical example where you have input nodes which actually do interact. And you want to have this kind of information in it. And the interaction strengths are learned and depend on the data itself. So that means that the transformer is ideal to use if you, for instance, want to fit, let's say, some forces which act on the system. And in case of the Ising model, you would typically feed in some early data on the energies of the system, depending on the spin values. And from that, you can extract this coupling coefficient. If you have gravitational force data, you would plug in the positions and the velocities of the different planets. And from that, you could extract the gravitational force. So that means that the interaction strength are learned and depend on the data itself. So transformers, then what they do is that they replace fixed interaction patterns by data-dependent couplings. So for somebody who is interested in this kind of, let's say, understanding the natural forces, this is actually very interesting. Now, after the break, I'm going to show you an example on how you can use transformers to solve differential equations. That's also one type of application which can be relevant for project number 2. So since you have these data-dependent couplings, it's actually pretty interesting for languages, long sequences, and images, and especially also scientific fields and operator learning. So when it comes to differential equations, what you're actually learning, and this depends a little bit on how familiar you are with solving differential equations. Are you guys familiar with Green's function theory? So the Green's function is an operator. So when you use transformers, you actually learn the Green's function for solving differential equations. So this is actually a very, very powerful method for looking at the complicated, let's say, partial differential equations. So there's a lot of, I would say, applications of transformers. And we obviously don't have time since I only promised a kind of brief survey. There's a limit to how much we can actually go through. Also, I have never done anything with language translations and so on. So I wouldn't be able to give you any examples here. So suppose you have this input sequence. So this could be the spins, which I mentioned. These examples could be words in a sentence. It could be spatial or temporal samples of a partial differential equation solution, which you want to train upon. It could be the spin values in this Ising model. And what the transformer does is it maps the sequence to another sequence of vectors. So that's the first step. Now, the next step is that we now have what is called the attention weights. And this is the essential part of a transformer. So for each position, there is a transformer so that you transform the data by having a matrix W. We're going to replace this as a matrix. So this contains parameters which needs to be trained. We have the input values, and then we have these attention weights. So let me try to explain what these attention weights are. So if we go back a little bit, the adaptive interaction through attention is the central part of a transformer. So this is it looks like an innocuous equation, but let's take a closer look at it. So the way you compute these weights, which we have here, is through two other set of parameters which link the input data. Now, what you have here is something which you have seen before. This is actually a lookalike of the softmax function. So it means that these coefficients, if I know, this is just a normalization factor, what you have here. I'm going to tell you why we have this square root of dk. But this becomes, again, parameters to be trained. These are parameters to be trained. So this is called the query and the key vectors. And that's the central mechanism of the transformer. So what you do then, so you collect the input, if we now put them into a matrix, then we can define, if you look at this expression for these Qs here, you can actually rewrite this as a matrix X times a matrix with the weights here, which need to be trained. This is the key data, as we call it. So we have the key and the query. And then we have V here, which is simply the object which you see forming these vectors. So that means that every column of this here is actually one of these vectors, Vj. And then the attention is actually us optimizing this object here, the softmax function, as a function of the query and the key here, and then multiplied by this so-called values which we have here. So this is normally called an interaction matrix. The softmax normalizes each row, and multiplication by V, that aggregates information. The matrix A, which is now the weights, that acts like a learned kernel or coupling matrix. And these are summed to 1. So it means here that the columns sum to 1. And this quantity Y, which we have, is a weighted average of these value vectors. So if we go back to the equation, we have this equation here. And now we are rewriting everything in terms of a matrix times a vector. So we would have this matrix multiplied with the VJs here. So the query is, what does the position I look for? And the key is something which says, what does the position J offer? And the value, what information does the position J contribute? So when you optimize this quantity, you actually you produce this self-attention. And if you look at the standard feed-forward neural network, this is the way a standard feed-forward neural network is set up. So this Y, and then you have fixed weights. These are fixed because you find a final set of weights. In contrast, when you look at this attention here, this Y of I is now given by this attention weight, which is then multiplied with the modulated input. So this becomes a kind of effective coupling. So if you think back to this case we did with the easing model, you could then think of that one as a way to model the coupling constant. So in standard neural networks, you have fixed couplings for every node, every hidden layer. Whereas here, with transformers, this becomes an adaptive coupling. And you can also have coupling between different nodes in the same layer. So this is actually why these transformers, so in a certain sense, you can look at the transformer, so it's still a nonlinear object, but you can look at that one as a way to actually encode an effective coupling between different nodes. And that's why they keep more expressive, they're more expressive. So in a convolutional neural network, what you have is typically a sum where you have some weights times some input values. But these parameters here, which you have this R, is actually given by a filter which acts only on a local part of the data. So the CNNs, they actually assume, if you think of an image and you want to classify whether this is a house or not, then the house has obviously very much localized information, like the windows are there, the doors are there, the roof is there. So that's a very local information. Also, you have assumed that there is a translation invariance, and we have a fixed size of the kernels. Attention, instead, is something which then becomes global, because this can actually couple all the different nodes you have. It's adaptive, and it's not restricted to local neighborhoods. But what you will see when you're going to run these codes, which I have online, it's that they are much more time consuming. So they are heavy to train. That's the price. Every time you want to have more expressivity, the price you pay is actually more CPU cycles or GPU cycles. If you look at an RNN, what you have then is the input to at a given time step, and then you have the information from the hidden nodes from the previous time step. So in a way, here, the information propagates sequentially. And this is something which is pretty natural if you're looking at the solution of a differential equation, or you have a time series. So if you have time series, then, and you don't have interactions which change from one layer to the next layer, then a recurrent neural network is actually ideal. Now, the problem when you do language translation with recurrent neural networks is actually that you need to encode or have the whole sentence you want to translate. And clearly, if you have many, many sentences, this can become a lot of data you have to store. And there is an explicit recurrence. So we have pretty explicit ways of keeping a memory of the information. So we know that one of the things we saw when we introduced the long short-term memory for recurrent neural network. So I'm trying also, as you can see, I'm trying to catch at least two birds with a stone here, because I wanted to say something about what we have seen till now and how that links with transformers. So the limitations is that the long-range dependencies are hard. You need to store a lot of data if you want to treat that properly. Training can be unstable due to exploding or vanishing gradients. And also a simple RNN is extremely sequential. So you cannot parallelize it. And that's obviously something which you don't want to have a set of an algorithm which cannot be parallelized. So the transformers avoid recurrence, and they connect all positions simultaneously through the attention. So the optimization of this softmax function is actually the quantity which then gives this coupling attention between the different nodes. So I see we are running a little bit over time. So after the break, I'm going to say a little bit more about the transformers. As I said, I promised you a kind of crash course here. We are not going to discuss codes. There are code examples in the on the course page, but we will not discuss them this year. But you can, if you're interested, actually made a code where I solved the Poisson equation, a differential equation with transformers. And I'm going to say a little bit after the break on how you can use them to solve differential equations. Yeah.
Is it because it scales better with language modeling? Or?
That's one of the things. But also, if you want to have the long-range dependencies, it means you need to save all the information. And that becomes time-consuming. You need a lot of memory to save that information. And that's the main drawback with standard recurrent neural networks. So it's more the long-range dependencies which are actually hard to train. So actually, people have been using transformers and train them on long-range forces, like the Coulomb interaction or the gravitational force, which has a long range. And they actually work pretty well. Okay, should we take a small break? Is that okay? And then we continue a little bit, and I want to give you a kind of overarching view on how you can use them to solve differential equations, which could be of interest for the second project, for those of you who do two projects. So before the break, we looked at this, the basics of transformers. And one of the basic equations which we actually end up optimizing is something which is a softmax lookalike. And in that case, we call this Q for the query and the key for the K for the key. And that means that when we now look at the data, there was a factor which was called 1 over dk. And the reason for why we do have that one is that these two quantities, they have a set of components with, if they have comparable variance, then typically these two variables multiplied with each other will have something which scales like the square root of dk, which is actually the standard deviation. And without normalizing, they can become pretty large. And that's why you actually scale with this quantity dk here, which is proportional to the variance of the product of these two quantities. And that is done actually to stabilize optimization and keep gradients in a meaningful regime. Oops. So the transformers, they actually use what's normally called multiple attention heads. So where we have the queries, the keys, and the values. And each one of them has its own optimizations, and then they're concatenated and linearly mixed. So different heads learn different interaction patterns, and one head may capture local structure, another may capture long-range dependence. A standard transformer contains then this multi-head attention, residual connections, a layer normalization, and position-wise feed-forward network. So it gets a little bit more complicated. So, but in a sense, it's still a deep network built from familiar components. So it has the attention part, and then it can have the standard feed-forward, plus some residual structure, which we haven't discussed yet. But in essence, what you have is something which contains at its heart a standard feed-forward neural network. So it's a permutation equivariant, depends only on pairwise relations, not on absolute order. And for sequence tasks, we also typically add positional information. And common approaches are actually some specific encoding. You can encode the relative positions, the distance between two. You can encode positions, etc., etc. So if we look at it, so we've been discussing loosely kernel transformations and kernel machines. And if we look at it, it actually resembles an integral kernel of the type where you have some k multiplied with some function f. And in a discrete setting, this attention acts like something like this, but where the kernel k is learned adaptively from the data. And it's normally something which can also link with operator learning. And I will going to show you an example of that. So let's go back to this Ising model case. Many of you have seen the Ising model. And in this particular case, you could think of these interaction elements as something which then gets replaced by these attention values. So then that means that you get in some information about non-localities. And you're assuming that the interaction, for instance, so this xj could then be the values of the spins in the specific position. And that interacts with another spin. And then we have the coupling constant here. So that means that you can have adaptive spin couplings in the Ising model. In the standard Ising model, you don't have it. But in principle, you could actually bake it in. You can have self-consistent effective interactions. So the transformers can actually be interpreted as a system with state-dependent interaction kernels. And that's extremely useful if you're going beyond just a static, constant interaction between the spins. I'm going to skip some of these slides here. But I wanted to say something about PDEs, because that could be of interest as a project number 2. So if you look at many of the partial differential equation problems, then they normally involve long-range dependencies. So if you're thinking of, let's say, an equation which involves something like the gravitational force has a long-range dependence. The same if you take two electrons which interact through the Coulomb interaction, that has also long-range interaction. So you have, for instance, you can have non-local operators, multi-scale dynamics, RNNs, and also CNNs. They are good for local structure, but transformers can actually naturally represent non-local coupling across the whole domain. And so that's why transformers are getting more and more used actually in scientific machine learning. So one of the big areas of application is actually language models and translation, for instance. But it's actually in the last few years, there's been a lot of attention on using transformers in scientific machine learning. Now, there is a clear reason why I have not included transformers in this course, as you understand from this one statement here, because the main application has been to other topics than, let's say, the standard methods which are encountered in physical sciences. But in the last years, this is actually something which has increased in attention. So I'm going to actually switch a little bit because I have some slides on actually this topic. And let me bring it up here. So I made some slides during the weekend, and I just wanted to bring these up because this is actually pretty a topic which is pretty novel. And the question is, can transformers be used to solve partial differential equations? So many of you did physics-informed neural networks in project one. Those of you are actually doing two projects. But then the question is, can we use this to solve differential equations? So this is a little bit tricky because we need to go a little bit around things. So the short answer is yes. So they can be used to solve partial differential equations, but not in the same way as you're used to. So when you have a classical finite difference method or finite element method, this is not the way it is actually done. So if you think of a differential equation, you can write, so if you look at this, this could be your second derivative, if you're thinking of the wave equation. So this could be the second derivative, and this f of x could be some given function. And the solution you're looking after is this one. So this g, which is normally called the Green's function, is actually the inverse of the operator which acts on the solution here. So think of this L. This L, which you have here, could be the second derivative of the function plus the first derivative. And then this fx of t could be a function which is equal to 0. Or it could be just be a fixed function which then defines your boundary conditions and the initial conditions. So this is a typical way you will see a differential equation being written. And this is a partial differential equation because we have more than one variable. So it means you need to have initial conditions and boundary conditions. Have you seen a differential equation written in this operator way? So if you do a course more in mathematical physics, this is the way you would often write it. And we know that the solution operator is actually this one. So that means that the transformer learns an approximation here. And a PDE defines a map from coefficients, some initial and boundary condition to a solution field. And the learning problem is actually your function, which is a transformer, which depends on some parameters and based on the input fields, which then can typically be initial and boundary conditions. So from a PDE point of view, this is normally what you call learning the inverse operator, which is associated with the partial differential equation. This inverse operator is normally called the Green's function. So transformers are then sequence-to-sequence model based on attention. For the PDE, what you reinterpret is actually the inputs with spatial or space-time grid points. The hidden states are local field values, and the attention weights become then the couplings between the points. And this makes actually transformers as natural candidates for learning non-local mappings. So just to give you an example, so a transformer actually computes outputs of this form, where these are the attention weights which are learned. And if you think of this with an integral representation of a partial differential equation, so this equation which you see here is a typical way you would represent the solution of a PDE. So when you took a course on partial differential equations, I assume that you have seen something like that. So it's a common way to rephrase it. And this is assumed to be a continuous function. And that suggests, if you look at these two equations here, it suggests that there is a correspondence between the attention and the learned Green's function, which is often also called the kernel. Now, I know that I'm throwing some of you into deep water, because if you haven't studied partial differential equations, you probably have not seen this type of equations. But this is a common way when you discuss the solution of differential equations. And the Green's function, then what the Green's function gives you is actually the inverse here, often called the resolvent. That's another name, or the kernel here. So many PDEs, they define solution operators of this type here. So you have some initial conditions, there's some coefficients, you may have some external force, and you have some initial data. So this could be the boundary conditions, this could be some additional term which you have, and this could be the initial terms. And from those, you can actually extract the final solution. And then a transformer can be trained to approximate this map. So one is not solving the PDE from scratch each time, but you're learning the family of solutions. So that's a different philosophy. So there are several ways transformer can be used for PDEs. Purely data-driven operator learning. You can do physics-informed training. And then you can also have some hybrid numerical machine learning methods. But there's a very nice link between the data-driven operator learning and a physics-informed training. So you train on supervised pairs, input fields, solution fields. So you can have some coefficients plus some term which forces, let's say, the object to move in a specific direction. So this would be the initial conditions and boundary conditions. And the output is then the PDE solution. And then the model approximates this with the Green's function. So in a sense, it's actually similar to neural operators. So some of you may have actually looked at physics-informed neural operators. That is also a very hot research topic. So the typical loss function is actually you taking the difference between the left-hand side and the right-hand side. So you can add, as we did with physics-informed neural networks. So this is a physics-informed transformer. So you can add the, if you go back to what we discussed with physics-informed neural networks, we had a loss function, which was a difference between the left-hand side and the right-hand side in a differential equation, which is what we have here. And then you have the boundary conditions and initial conditions. There can be conservation laws, which you want it to obey. So these are all things you can bake into a cost function. So it's pretty similar to what you have with physics-informed neural networks, but you have transformer architectures instead. And they're actually being used now with several classical PDE solvers. I'm not going to read everything. So this transformer actually acts as a kind of surrogate or correction model. They may be attractive because they can capture long range and non-local interactions, which can be difficult in a standard finite element or finite difference solver. You can solve parametric families of partial differential equations, and you can actually also add irregular dependencies more flexible. So I'm not going to say everything here. There's a lot of stuff, and you have if you think of some of the comparisons, the most obvious ones which we have discussed here is pins, which enforce the PDE residual directly. You have Fourier neural operators, which some of you actually have been looking at, And then the transformers, which use attention to learn flexible non-local mappings. And each method has strengths and weaknesses depending on the structure of the PDE. So if somebody's interested in taking what you did for the first project with pins, and you want to continue along that line, a very nice research line is actually to enlarge project one to include transformers. So that's one possible. So I'm mentioning this because I also want to show you that this is a possible path for the second project, if you wish to stay in the world of partial differential equations. So I'm not going to say everything. In the end of the slides, there's also a connection to the Green's function, a more clear one. And there is an example with the Poisson equation, because formally the solution, if you think of a PDE, is something which you, if you want to write it formally, you can write it like this inverse operator. And in many cases, this becomes equal to this function here, where G is the Green's function. And that's why transformers can be interpreted as a kernel Green's function. And in one case, and I have an example in the, together with today's Jupyter notebook, there is an example where I actually look at the Poisson equation. And I solve the Poisson equation with the finite difference methods. And you won't be surprised that when I do that in one dimension, these methods are superior to transformers. Actually, the finite difference goes like this. You can barely glimpse before you have the solution. And the transformer goes on for minutes and minutes and minutes. So for low dimensional problems, there is no way you can compete with many of the established methods. But when you go to higher dimensional problems, this is when they become interesting. And also when you have long range forces. So you could take a discretized f of x as input, you output a predicted field, and you learn the effective kernel which links the two. So the transformer is not solving the PDE in a classical term. It learns the mapping from F to U, or more generally, it actually, through the weights, this attention function, it actually learns, depending on this input, the boundary conditions, the input, and an external force which acts on the system, it learns a solution. And this means that it learns an approximate Green's function or response operator. So the main role is actually to learn the solution operators and approximate the Green's functions. This is basically, so you're not solving a differential equation like you do with pins, but you're actually learning the solution operators. And if this is of interest, then transformers are actually very interesting for this type of problems. So this was a pretty rough digression here. So let's, I just wanted to say a kind of a summary, a little bit. So let's just summarize a little bit what we have been saying about transformers. And there's obviously much more to the picture than we have time to cover here. But I hope this gives some kind of attention or interest in the topic. So one of the reasons why they are so popular is that you can have global interactions. It's easy to parallelize. You can have a strong scaling with the data and model size. And it's a pretty flexible learned interaction structure. And they perform especially well for us doing physical sciences when you have long range correlations. And this is also a very powerful thing when you're looking at the language translation, because then you want to have, if you think of a sentence in German and a sentence in English, the way you put the verb is actually different in English and in German. In German, you would typically have the verb at the end of the sentence, which means that you need to have the whole sentence when you're making a translation from German to English. So that means the kind of long range correlations actually do matter. And the flexible learned interaction structure is actually very important. And they're actually powerful models for systems with rich non-local interactions. If you look at standard deep learning, they are not separate from deep learning. They're actually a modern architecture with deep learning. So everything we have studied till now neural networks, recurrent neural networks, CNNs, etc. They have basically many of the same features. You have the layers, nonlinearity, residual connections. You have gradient-based training. So what is new is actually the central primitive, as called, is the self-attention, rather than convolution or recurrence. That's the basic main difference here. The strength and weaknesses is also important. When somebody says that my method is much better than all the other methods, that's when all alarm clocks should be turned on and you should be suspicious. Every method has their pros and cons. So the strength is it's highly parallelizable. This is something we haven't discussed. It's adaptable to many data types, and it captures long-range dependencies. So if this is something, yeah. Oh, so something which is very highly parallelizable is, for instance, the integration. So when you discretize an integral, what you can do then is that you can split your integral in many small parts, and then every process calculates its own part. So that's normally called embarrassingly trivial to parallelize. But when you have a differential equation, then you have connection between different nodes or different points, and that means that you have lots of communication. So if you want to parallelize, for instance, an eigenvalue solver, then you actually need to have a lot of communication while you run the parallelization. And then it's less trivial. So you have some methods which are really trivial, where you can simply separate it and you can let every sub-process work independently of the other ones. And when everybody has finished, you just collect all the data. And in case of an integral, you just sum up all the small integrals, and then you have the final integral. So that can run, that's a very easy case to parallelize. And you get a speed up of 100%. Because you have basically no communication between the different processes. So it's very data hungry. That's one of the drawbacks. And it can be less structured than many of these kind of domain-specific architectures. So what people often do is that they use some kind of hybrids between some well-known science problems and then the attention mechanism. So in scientific machine learning, when I say scientific, I have to be a little bit careful because I'm often thinking about natural science. So it's being used now in PDEs, been used in turbulence modeling, climate and weather forecasting, operator learning, also in quantum many-body calculations. So the central attraction is that attention provides a flexible way to encode interaction across scales and distances. So if that is important, then transformers may be something which would be relevant. So if we do a summary here, so transformers are actually deep neural networks built around self-attention. And the standard feed-forward neural network used fixed dense couplings. CNNs use local kernels. And then RNNs use actually a sequential recurrence, whereas transformers use adaptive global couplings. And this makes them especially powerful for non-local and multi-scale problems. So that's, if this is a kind of problem you're interested in, then transformers may be actually of interest. Okay. I was a crash course in transformers. I realized that this is something which in the next years is going to take more place, because it's a field which is becoming more and more important in natural science as well. So actually, I'm remodeling this course every year, because 2 to 3 years ago is archaeological time in machine learning. It's in a way, it's a kind of stressful course to teach because you have to change the content every year. And next year, this part will actually be expanded on transformers. But if you want to explore it, I actually recommend taking a look at Rashka's textbook, which you have access to, and look at chapter 16. That gives a lot of examples. And let me also mention, so let me just bring this up because I have a So let me just bring back the screens here. Now I have to find out where I have my, here we are. So if you go into the lectures from this week, you go to the Jupyter Notebook where I have the Jupyter Notebook, you will find an example on how I use transformers to solve the Poisson equation. So if you wish to study a little bit, I mean, take a look at it. But just as a warning, this code is so slow. So if you have some time to waste, this is an ideal thing. There is also another example, which I put up here, where you learn the coupling in the Ising model using both a neural network and transformers. This is actually an example on how you can use deep learning methods to actually learn the interaction strength of a model. So these are just examples on two types of applications, besides those which you find in the weekly material. Now, if you go to Rashka's text, on the other hand, and this is, there's a link directly to the different chapters. So if you go into, and you have this link in the textbook, and in chapter 16, you will find the Jupyter notebooks, which are discussed in the textbook. So if you wish to play around a little bit and you wish this to be an example, I'm actually going to make a variant of project 2 for those of you who are interested, which is based on transformers. If you wish to explore that. Okay. So now I wanted to start with the final topic for the semester, which is generative models. And in a certain sense, to me, these are much more interesting machine learning methods, because when I use, let's say, the discriminative ones, which we have discussed till now, you typically are interested in predictions, making predictions and finding correlations in the data. Now, with generative models, you produce a probability distribution. You train a probability distribution, which means then that what you end up with is the capability of making predictions. The probability distribution allows you to find correlations in the data as before. But with a probability, you can say something about causality. What is the probability of A given B? And it also gives you the errors in the parameters. So it's a very powerful method, set of methods. And this is what we are going to spend our time on for the rest of the semester. So I want to give you a little bit of the feeling of what these methods are. And then after the break, we are going to dive fully into Boltzmann machines, variational autoencoders, diffusion models, and other methods. So let me just bring back the slides again. No, not that one. Stop, I have to. No, wait. Where did I have it? There we are. Can those of you online see it as well? So, generative modeling is an important branch of machine learning that involves training a model to produce new data. So what it means, suppose you have a data set containing photos of horses. Then you can train a generative model on this data set to capture the rules that govern the complex relations between pixel and images of horses. Then you can sample from this model to create new realistic images of horses that did not exist in the original data set. So some of these methods are actually the more popular ones used in actually image generation. So this is something which I took from the textbook of David Foster, and you could then train on images of horses, you produce a probability distribution, and then you can generate new types of horses. So you can make pink horses, yellow horses, horses with 10 legs, etc., etc. The kind of horses you want to have. So I wanted to say a little bit about, so what we have done typically till now about discriminative modeling is actually based on us having some training data, and then we want to discriminate. That's why we often call this discriminative. So we want to train on a specific images, and in this case, it could be Van Gogh paintings. And then we want to, when we feed in a new painting, we want to say whether this is a Van Gogh or not. Just to give you an example of how we could use a CNN. So we could train a convolutional neural network on paintings of Van Gogh, and then use that one to discriminate on new paintings, whether they are Van Goghs or not. Okay? So what we are going to look at now are several of these discriminative methods. Now, if you look at this slide here, this slide contains essentially what is going to keep us busy for the rest of the semester. So you have the explicit densities. So you could have a Boltzmann distribution, which is an explicit density. The problem, however, with an explicit, yeah. So you have an explicit mathematical expression for it. So if you take the Boltzmann distribution, you know exactly what it looks like. Yeah. The problem, however, with a Boltzmann distribution is that you have a normalization factor. And that normalization factor can be a monster to calculate. So that means that you want an approximate density. So even if I give you a probability distribution for finding, let's say, 100 molecules in specific positions, and you have the analytical expression, this may be so complicated to calculate from that you want to approximate it in one way or the other one. So that leads to approximate densities. So it's always, I mean, there's a kind of trade-off between the type of problem you're interested in. So I can set up the explicit probability distribution for the Ising model with a Boltzmann distribution. But if I have more than 10 or even 10 or 20 spins, I cannot calculate directly from it within a reasonable time. So then you're often looking at the approximate densities. And that leads to methods like variational autoencoders. Energy-based models are Boltzmann machines. And then we have diffusion models. So we are going to cover methods like the ones you see here, the variational autoencoders, energy-based models, diffusion models. These are central models in generative modeling. We are going to say something about implicit densities. Actually here, you don't extract the probability distribution. So you have an explicit density, but you need to approximate it. Here, you don't care about the distribution, but you have still a generative method. And these are called generative adversarial networks, which we will also discuss. These are very popular methods. And the textbook by Foster, which we have also access to, covers these methods, not in mathematical detail, but it contains a set of Jupyter notebooks, which you can download and try on your own laptop. And this textbook uses actually TensorFlow. I will try to provide you both with TensorFlow examples and with PyTorch examples on how you can do this. So the thing I wanted to say a little bit about before, so I'm going to come back to this a little bit later. So let me just skip it. And what we are going to look at in quite some detail is energy-based model, which start with the Boltzmann distribution. Because if you're familiar with the statistical physics, then the input is actually the energy of the system. So that's the argument to the Boltzmann distribution. We are going to look at variational autoencoders, which is a follow-up of the discussions of autoencoders. And then we are going to look at diffusion models and generative adversarial networks. If you have other models you would like to discuss, like if we get time, we may say something about autoregressive models and normalizing flows. Yeah. Okay. So we can, if we get time, I could replace generative adversarial networks with normalizing flow models. So, I mean, come with your preferences. I mean, I would try to adjust but the three ones I will start with first are actually these ones. And then I will rather either say something about normalizing flows or generative adversarial. I do that actually, did you? Yeah, I do, yeah. So that's something which we also can focus on, yeah, yeah. So that will be, so we have roughly 6 weeks after the break. So we should have 6 times 2 hours of lectures. So we should get some time to look at it. So let me give you the basics. And then we are going to set up what we are going to define as energy models, which are essentially Boltzmann machines. And Boltzmann machines were actually very popular before CNNs came on the market. So people actually use Boltzmann machines to recognize images. And this is one of the precursors of modern machine learning. And Hinton, who got the Nobel Prize last year in physics, was the one who proposed the Boltzmann machines as a machine learning method. And they're pretty cool, actually. I have done a lot of work on Boltzmann machines, and I really like them. But you see, the basic idea is that we want a probability distribution. That's what we want to train. Then, what this probability distribution is going to contain is a set of variables. So this could be the position of a particle or something else. And what we have in addition is a set of parameters which then are needed in the optimization, which can be the biases and weights of a neural network. And then this leads to hidden variables. So the X's are the so-called visible variables. So I'm going to bring in some elements of statistics before we move on here, because there are some key elements which we need to say something about. So let me switch to the whiteboard for the rest of the lecture. So let's do that. So what we want is, suppose we have a domain, so this is generative methods, and we will dive fully into these methods after the break. So what we want with a given data set, so this is a domain of events, x0, x1, xn minus 1. What we want then is a probability distribution where we now have assumed that all these variables are identically distributed and independent. So that means that the probability distribution is simply the product of all the individual probabilities. So we have a P of I, and this contains X of I. So each one of them has the same probability distribution. However, we are going to train a network which will then also have some parameters. So in principle, what we will end up with is a probability distribution. If we now take these single ones, I'm just going to take away the P of I, but we are going to train a probability which is going to be given by X of I. There is going to be a parameter, H of J, and then we have a set. So H is called a hidden variable. It's also assumed to be a stochastic variable, hidden variable. And it's also assumed to be independent and identically distributed. And then the theta are actually the parameters of a network. Okay. Now, the first model we are going to meet is normally called an energy model. And this is actually based on the Boltzmann distribution. So we are going to assume that this P of xi and then hj and these parameters theta is now given by some function which depends on x and h and these parameters theta, and there is a factor here. And now I'm just borrowing a labeling from statistical mechanics. And if you go to, for those of you taking statistical mechanics, this has a special name. Does anyone remember that? It's called the partition function. But it is nothing but a normalization factor. It's a normalization factor. So this is the partition function in statistical mechanics, but a better name is actually a normalization factor. Because we normalize the probabilities so that the sum of all the probabilities is equal to 1. So that means that if I sum over all these guys, of P, of xi, and I sum over hj, so I sum over xi and hj, as a function of theta, this is normalized to 1. That's a standard. Now, the function c of theta is given by xi, and then we have x element in the domain x, and we have h element in the domain h, and then we have this function f of x of I, h of j of theta. So just to give you an example, which you have seen before, if you look at the Ising model, this is a famous example, then the energy is given, the total energy is given by this constant, and I'm summing over nearest neighbors, and then I have the spin Si and spin Sj. That's the Ising model. That means that my partition function for the Ising model, or the probability for being at a given temperature T in a state, in a specific energy state, I, is given by E to an energy minus EI divided by kBT, Boltzmann's constant, divided by T, and then I have the partition function at a finite temperature. Now, this C of T is nothing but the sum over all the possible states which we have available of J of E of minus EJ kBT. That's a so-called partition function. Now, one of the beautiful things in statistical mechanics, this is a microscopic object. It tells you about the energy from a microscopic point of view, the basic interactions between the spins. And from that function Z, you can derive all thermodynamical properties. So when I took a course in statistical mechanics, that was an eye-opener. It's actually my favorite topic. There's a digression, because I started my studies with chemistry, and the chemistry teacher the first semester gave us all these thermodynamical relations. And then I asked, what does Gibbs free energy mean? Or Helmholtz free energy? It's just an equation, use it. That was the answer. But then in statistical physics, you could actually derive all these equations directly from a normalization factor. And that is beautiful. But this is a digression, actually. So, but the thing is, you see why these are called energy models, because the function which we are going to operate on is this function f. And this function f you see here could actually be, and it's going to be, given by something which looks like this. So what we are going to have, and this is where we stop now. So this function f of x of I, h of j, these are parameters, and theta, this is now given by some E with some energy which depends on xi Hj of theta. And that's why they're called energy-based models. It doesn't need to be the energy. Actually, this E, and this is something which people have been using recently, and it's extremely powerful. This E could be a convolutional neural network. It could be a recurrent neural network. It doesn't need to be the energy. And this has been extremely successful actually as a usage of generative methods. Yeah?
But do you know what is the output of CNN or an RNN?
Oh no,
Would it be a probability distribution or like a label?
it's a probability, because your probability, the P which you have, is going to be given, so this P of xi of Hj of theta is now going to be given by this E to the minus E of xi Hj of theta divided by the normalization factor, which now depends only on theta, because you have integrated away. Now, what you see here, and I wanted to stop here because you see the problem here. So the problem resides in the normalization factor, because in that case, you need something which depends on all the x's and hj's and the parameter theta, because the recipe we are going to use now is called maximum likelihood estimation. That means that our cost function is going to be the probability. So what we want at the end, we don't want to have something which depends on the hj's, but we want something which depends on xi as a function of theta, and that is obviously sum over all the h's. And this is called the marginal probability. So at the end, we want this object here. So we are going to train with a neural network or deep learning method. We are going to train this probability. This is what we want. And you see immediately that what we are going to do is actually to optimize the probability as a function of the parameters theta. Now, the optimization in this case is not a minimization, but a maximization, because we want to maximize the probability. Nobody wants to minimize the probability. You don't want to have something which gives you zero probability. You want to have something which gives a maximum probability for finding this variable. So the problem we are going to face then is to maximize this guy. So we are going to take the log of that quantity. But when we take the log, we are going to have the difference between the numerator and the denominator. And the denominator is going to contain the normalization constant. And that's where all the evil is hidden, because this contains a sum over so many variables that it becomes almost intractable. But on paper, as it stands now, this looks very nice. So we are going to maximize the probability as a function of these parameters theta. So this is basically what we will start with. So after the break, we jump into Boltzmann machines and derive them, look at how we can encode them. Then we move to variational autoencoders, diffusion models, and then we will see how much time we have left. Okay? These are my favorite methods. You can probably see that from the excitement which I have. Okay. Okay, see you. Take care.